We'll hand over here to Shelbee in just a second. She will talk about the top challenges and considerations for adopting machine learning at scale. And then after her talk, we will have Mani and Farouk joining us, and they will talk about hierarchical forecasting with scikit-hts and Amazon Sagemaker. So pretty exciting agenda today. And with that, let me stop my screen share and hand it over to Shelbee. Shelbee, if you want to briefly introduce yourself, maybe a little bit as well, and then take it from there.
Sure, thank you both. So I'm Shelbee Eigenbrode. I'm an AI/ML specialist solutions architect at AWS. And today we're going to talk about some of the top challenges for adopting machine learning at scale. And then for this, I'm going to focus on the challenges that I see across organizations, keeping in mind that I do tend to focus quite a bit on large enterprises. So some of the challenges that we talk about here may be a bit more specific to large enterprises, but also applicable to smaller organizations or startups even. So in this session, I'm going to focus on not only the top challenges that we talk about when adopting machine learning at scale, but also some of the considerations for approaching those challenges. So I'm going to share my screen. The most humbling part of an event is sharing my screen. All right. Can you see my screen okay? Hopefully.
Yes.
All right. Hopefully it says going from.
It does.
All right, perfect. So to get started, we'll talk about what we mean about adopting machine learning at scale. So what does that mean? So essentially, we're looking at how do we go from operating one or a handful of models in production to ultimately being able to operate multiple models in production. So in this case, we're talking about operating tens, hundreds, or even thousands of models in production, typically while serving a larger user base that may include, millions upon millions of users. And operating at this scale usually has several challenges that require additional considerations. And that's what we're going to kind of focus on today. So when we look at the top challenges in scaling machine learning workloads, those challenges typically fall into one of these three categories that you see here. So they're either related to people, process, or technology. And sometimes these overlap quite a bit. So as an example, a challenge in the area of process may cause another related challenge in technology as well. So just keep in mind that as we go through these challenges within each of these areas, they aren't necessarily mutually exclusive from each other. And we'll talk through some of those a little bit today. So let's take a look at each of these areas in a little bit more detail. And we'll start with people. So some common scaling challenges that organizations see in this area typically include things like a lack of executive sponsorship, a gap in skill sets of those that are needed to build, deploy, and operate machine learning workloads. A typical machine learning workflow, as many of you know, it covers many tasks around data processing, model building, model deployment, and then ultimately ongoing operational tasks. And the fact that these tasks need to be included in a workflow that requires multiple personas across these tasks creates some additional challenges that we see around the dependencies and often the competing needs and priorities between those personas that are needed. And then finally, it's often the case that organizations typically have heavily siloed teams. They are not only siloed by function, but like such as a separate R&D group and a separate operational group, but also separated across the life cycle of the machine learning development life cycle. So having said that, let's take a look at each of these areas in a little bit more detail and talk about some of the considerations within each, starting with a lack of executive sponsorship. So, and I fully really believe in grassroots efforts within an organization as a way to drive innovation. And a lot of those bottom-up movements really are what often helps get those first few models into production and get those out the door. However, it is really difficult to scale those grassroots efforts and begin to adopt the use of machine learning at scale as part of any kind of overall strategy without having that top-down executive support. And then this level of support is really key for a variety of reasons, but a few key reasons are to provide project funding, right, is one, as well as establish prioritization across the organization. So it's also key to have executive sponsorship to ensure that machine learning isn't just about doing what's cool and what's new, but that it is really aligned with the goals of your business and it's being used to drive very specific measurable business outcomes. And then finally, executive support can often be needed for organizational alignment as well. So I mentioned before, establishing prioritization, and this often includes getting buy-in or setting common goals for the key stakeholders that are really ultimately required to take that model from ideation to a model that's deployed, operating in production, and driving business value. So once we have that top-down sponsorship and alignment, another key challenge is often around how to execute against those projects to drive business value. And this brings us to the next common challenge that we talked about, which was the gaps in skill sets across teams. So as many of you know very well, machine learning workload encompasses more than just a model. So, there's the data that's needed to train the model, there's the algorithms, the frameworks that are needed to train models, the underlying infrastructure or the managed services that are often needed to train and deploy models, the tooling and services that are needed for the ongoing operation of the workload, and then ultimately often integrating that model into some type of client application that'll then consume that model. So all of this requires varying skill sets across different domains like data science or analytics. And what this often means is upskilling existing teams combined with some level of cross-training. And this cross-training isn't intended to, have everyone become an expert in every aspect of the machine learning development lifecycle, but really just to give high-level knowledge to the personas that are really involved in that end-to-end workflow so that they're familiar with some of the technical considerations that need to be considered early on in the model building phases and of your machine learning development lifecycle. So as an example, I'll often meet with data scientists and we'll go over high-level concepts such as microservices or model deployment considerations, or maybe even containers. And then on the other side, I'll meet with DevOps teams or maybe like MLOps engineers, whatever kind of we're calling them, the word of the day is. And we'll talk about things like the basics of machine learning to help in building out machine learning pipelines so that they know, what does it take to build and train a model? What are the artifacts that are produced? That's ultimately needed in building kind of those end-to-end automated workflows. And again, the intent here is to just provide enough level of information so that each persona can ultimately consider a path to production early on in that ML project. And there's also often a need to ensure technology-specific skill sets as well. So I'm not focusing on AWS technology specifically in this session. However, of course, we're partial to AWS. So including some resources here that are either free or they're paid training that are just really good for upskilling teams. And, many of the concepts that are really talked about across these courses apply regardless of the technical implementation that you choose or the tooling choice that you choose. So inside skill sets, I talked a bit about the different personas and then the span of skill sets that's really needed to ultimately bring a model from ideation to production. And this kind of brings us to our next common challenge, which is the fact that multiple personas are indeed required to ultimately deploy a model. And these personas don't necessarily represent individual people, right? So that this may not be what your team looks like. A lot of times, one person can have, the roles and responsibilities across these different personas. But it is entirely possible, that one or two people may fulfill all of these roles within each persona. It's more about the tasks and the typical responsibilities that each of these personas does as it relates to the machine learning development lifecycle. And it tends to become more challenging in a common scenario that we see where there are multiple teams and personas that fulfill these responsibilities. And it can often be the case that each of these personas is part of a heavily siloed organization as well. So that means a lot of handoffs. So in this case, the dependencies that exist across a typical machine learning workflow become a challenge, especially when each persona has different or competing needs and priorities. So as an example, if you're dependent on a DevOps or platform engineer to deploy that model into production, but maybe that team is also overloaded and they're supporting other existing workloads, you can quickly have a bottleneck on the deployment process. So to help address this challenge, we should consider establishing cross-functional teams with shared project goals as a way to ensure that all key personas are aligned throughout a project and that each persona shares goals that align with providing a path to production for that model or that machine learning use case. So in addition to these cross-functional teams, you want to ensure that you're also able to automate as many tasks as possible, including those handoffs that we talked about between personas and between the steps in the machine learning workflow. So as an example, if a data scientist is dependent on curated data sets, and the current process includes having a data scientist open a ticket or contacting the data engineer every time new data is needed, there's likely to be a delay in the handoff each time between those different steps. So you want to look for ways to scale those handoffs. And you usually do this through patterns that automate things like data governance, data access. So we just covered some of the challenges and considerations across the area of people. So now we're going to switch gears and move on and cover some of the scaling challenges that are more specific to process. So some of the scaling challenges that we often see in the area of process include not having a defined ML strategy, not having a defined data strategy, and struggles with the ability to enable innovation for model builders while still balancing the traditional needs of IT, such as security, deploying reliable workloads, or even ensuring a cost-optimized solution. And then finally, we see challenges with how to better streamline or manage the multiple manual handoffs between personas, similar to what we talked about before under people. But again, each of these aren't necessarily mutually exclusive, and we'll talk about how it relates to process. So again, let's take a look at each of these in a bit more detail to talk about some of the considerations on each, starting with a lack of a clear machine learning strategy. So an ML strategy typically includes multiple dimensions, but one of those dimensions includes the process for choosing and prioritizing the right projects to work on. And this can be difficult for a number of reasons. AI and ML provide really exciting ways to address business problems and provide insights that weren't previously available. But sometimes the excitement around everything machine learning could potentially be gets in the way of choosing what are the right projects to actually work on. Sometimes you get in brainstorming sessions on different ways to use machine learning to solve business problems. And there's kind of a difference in between, what we can do and what we should do. So we want to make sure that we're choosing projects that are technically feasible. They provide the expected return on investment. They can provide business value quickly. And most importantly, they're driving measurable business outcomes. And there's different methods out there for choosing the right projects, but one includes considering a project or use case across these key areas you see here. So across data readiness. So does the data that you need to solve the problem exist? Is it clean? 2, business impact. So can we actually measure the expected impact to the business? And then finally, ML applicability. So what is the chance of success based on the state of the art and skills within the team? And again, not every problem is a machine learning problem. And this kind of brings us to the final note, which I mentioned before. It can be really excited when you start getting machine learning as part of your strategy to drive business outcomes. And, sometimes you get into those sessions where you're talking about the art of the possible. But what we really need to do often there is scale back to what really should be done and what we should be focusing on to make sure we're prioritizing the right projects. And ideally, it's those use cases or those projects that are relatively high in those 3 areas that we see here, and that we can use to drive business value. So we talked about data readiness as part of an ML strategy in determining the right projects to focus on. And this brings us to the next common challenge that we see here. And this is when we're talking about scaling machine learning, not having a defined data strategy can become a key blocker to adopting machine learning at scale, because as you know, data is really key in being successful with those machine learning workloads. And a data strategy can get pretty involved, but some of the questions around your data strategy, the questions there in orange are some of the questions you should be able to answer and consider, ensuring things like, are you collecting the right data? How are you curating the sources of your data? Are you implementing the proper data classification strategies, providing governed access to that data. And establishing your data strategy is really a key first step when adopting machine learning at scale. You want to make sure that data is accessible and you're breaking down those data silos or data hugging as much as possible. But of course, that also has to be balanced with things like regulatory or corporate security requirements, which is where the concept of guardrails comes into play. To ensure that your data is accessible, but you're also ensuring that data access is only given as needed and sensitive data is obscured when possible, so you have proper governance and controls in place. And this really leads us to our next challenge, which is the challenge of enabling innovation so that data scientists can really innovate and build models while still balancing the needs of IT. And we talked about a data strategy that includes security and governance considerations, which is one key example. But there's also other considerations such as reliability. So how can you ensure that a trained model artifact is protected against modification or inadvertent deletion in the event of the need to recover, right, to ensure reliability? Or how can you implement cost controls? So some things to consider when you're looking to balance these needs include, first, ensuring that data scientists really have that ability to innovate in an environment that is controlled and it has the guardrails in place. And then second, enforce not only traceability, but also operational efficiencies by creating repeatability through machine learning CI/CD pipelines. So the next challenge here under process is common under people, but it's having those manual handoffs between personas. And we talked before about the challenge of these personas having competing needs and priorities, which delays the ability to quickly deploy new machine learning use cases. However, another challenge that's more specific in the process area is the manual handoffs that often happen between personas, which also impacts the ability to quickly build and deploy new machine learning use cases. And it's often common to have those siloed teams where the output of one of the tasks in this machine learning workflow, they're not only manually created, but they're also manually handed off or kind of thrown over the wall to the next persona that's involved in executing the next step in a workflow. So to avoid these manual handoffs, one key consideration is to automate the tasks within a step, but also automate the handoffs between personas. But automation alone, can help with speed, of course, but there's often a need to have additional checks and balances that happen during those handoffs to ensure that you're not just automating, but you're able to automate with some guaranteed level of quality. So looking for opportunities to automate any of those quality gates that provide assurance that not only is the output of the task ready, but it also meets a minimum requirement to proceed into that next step in the machine learning workflow. So as an example, before a data scientist is able to promote a candidate model for production deployment, a common quality gate may be to automatically record model evaluation metrics that ultimately need to meet a minimum threshold before moving that model to the next step in model deployment. So we just covered some of the challenges and considerations in the area of process, but now we're going to switch over to areas and cover some of the scaling challenges that are really specific to technology. And this is often an area that a lot of us gravitate towards first, right? Because we're all technologists, we all gravitate towards technology. Maybe people and process is more fluffy. But really, I'd argue that technology is often the easiest part, right? It's obviously easy, or it's often the easier challenges to overcome. People and process are equally probably more important to make sure that those are aligned as well. And those are often the more challenging challenges to overcome. But in the area of technology, some of the scaling challenges that we see here are identifying the most appropriate service or tool to use to solve a specific machine learning use case, being able to provide a consistent and repeatable path to production. Third, how to integrate your model development tooling choices with existing tooling, which is often the need. Fourth, how to integrate your models with client applications so that your model can actually be consumed. And then finally, once you have your models deployed, how do you then operate that model in production? How do you monitor it? So again, let's take a look at each of these in a bit more detail. And we'll talk about, again, some considerations on each, starting with choosing the right service or tool, or even the right approach for a given use case. when ultimately we want to be able to drive a path to production that can quickly begin to add business value. So part of that includes determining whether AI or machine learning is even the right technology choice for a specific problem. So we talked about this before in the context of an ML strategy and choosing the right projects under ML applicability. But from a technology perspective, it's possible that some use cases are better solved by simple analytics approaches. Next, if it's tempting to really want to go ahead and build that model from scratch, but we do also recommend using AI services or pre-trained models where you can to establish those quick wins early. AI services like Amazon Recognition or Personalize, they're typically purpose-built and they allow you to interact via simple API calls with pre-trained or even custom models. And they allow you with custom models with more AutoML capabilities. So in AWS land, like I mentioned, we have services like Amazon Recognition for computer vision. We have Comprehend for natural language processing. And using these purpose-built AI services allows you to have those quick wins on machine learning problems that have already been solved, while focusing your data scientist time on those hard to solve machine learning problems. Also, the time it takes to set up and manage your environments that can be used for model building and deployment isn't trivial. So we always recommend taking advantage of managed services where the underlying infrastructure is managed for you. And you're provided with features that can help you accelerate that end-to-end machine learning lifecycle. So again, at AWS, we have ML services, or more specifically, Amazon Sagemaker, that's designed to do exactly that. And then finally, depending on the use case, it can take a significant amount of development time and iterations to get that desired end state. So consider simple approaches that can be delivered as a minimal viable product and then still drive some business value while you continue to iterate on that. So the next challenge I often see is in organizations where there isn't a clear path to production. So this can be for any number of reasons. In some we already covered, like not having cross-functional project teams with shared goals in place, or those manual handoffs between personas. But there are also technical implications where there isn't a consistent or repeatable mechanism in place to perform all of the steps that are ultimately required to, as part of that machine learning workflow, to orchestrate the sequence and the conditions in which those steps execute to get a model to production. So the result is typically delays in getting that model deployed. Sometimes it means rework inside the lifecycle, and it often means not catching an operational concern early, because all of those quality gates to get a model to production aren't even identified, let alone established as part of your automated pipeline. So to be able to scale your machine learning workloads, you want to implement machine learning pipelines that automate the tasks across these steps in your workflow, as well as provide over orchestration of these steps. And ideally, you also want to be able to incorporate CI/CD practices like source control and version control to really ensure that end-to-end traceability and consistency. And then the tooling and services that are available in this area are really improving. So you have services like Amazon SageMaker projects or pipelines that aims to make building out these pipelines easier by automating some of the integration work that's typically needed to really be able to stitch together these model build and model deployment pipelines. The other challenge in a path to production is often the handoff between model build and model deploy phases. So one of the first questions I typically ask organizations or teams that are looking to scale is if they have a model registry in place. And the reason a model registry becomes so important is it contains key metadata about how a model version was built, how it performed, and how it's deployed. And it can almost serve as a contract between personas and phases in your machine learning workflow, while also centralizing the management of model versions as you begin to scale from a few models in production to hundreds or thousands. So the next challenge I see is integrating your machine learning workflows with existing tooling. And this is more common in organizations that have a standard set of IT services or tools that are used to deliver software or even applications to production. So this can include things like automation or CI/CD tooling, container scanning software, repository managers, monitoring or ticketing systems, just to kind of name a few. And then you also have an array of tools and services that can be used to build and deploy your models on top of all of that. So applying traditional IT tooling and services that are used to deliver software to your machine learning models can be a challenge, especially when there's a lot of variation across teams. So sometimes this means that you need to make a decision between complete freedom of choice in the tool or services that you use, or trying to standardize and simplify where it makes sense to simply allow you to move faster. So the next challenge here is how to integrate models with client applications, or really answering the question of how will your model be consumed? And this could mean, the prediction results will be consumed ad hoc or from a persistent data store, or, for those batch use cases, or it could mean they're going to be consumed in real time via client applications. So understanding how your model will be consumed early allows you to plan for integration with any client application, as well as plan for how your deployment pipeline is going to work. And the typical recommendation here is to plan to package your model for consumption as an API. So it almost becomes its own microservice, where some of the complexity of maybe the data pre-processing, data post-processing can be abstracted and encapsulated in that microservice for your consuming applications. So there are a lot of traditional IT considerations for model consumption, such as how those clients are going to authenticate, or how do you ensure your model is hosted on highly available infrastructure. For this, again, we go back to those cross-functional project teams, identifying those needs up front, and identifying that integration path early on in your project. And then the final challenge that we'll cover under technology is around the ongoing management and operations of a machine learning workload. And this is often a challenge because monitoring and managing a machine learning model in a production environment is often very new to the teams that only have a few models in production. Oh, so sorry. Apologize. That only have a few models in production. So the challenge is usually in identifying, what do I need to be considering? So things like, how will you monitor your model? How will you deploy updated models? And how will you manage model versions at scale? So for this, some considerations, and these are just some of the considerations, are just make sure that you have a plan in place to identify how you're going to monitor your model for, things like concept drift, data drift. How are you going to implement a retraining strategy? Ideally an automated retraining strategy, but some type of retraining strategy when your model does decay over time. Also implementing automated model deployment pipelines. So finding a consistent, repeatable mechanism to deploy your models, new models and updated models. And then implementing a model registry so that you can efficiently manage multiple model versions as you begin to scale from, having a couple models in production to hundreds or even thousands. So we just went through some of the common challenges and considerations for scaling machine learning across people, process, and technology. And as I talked through it, you probably saw where there really is a need for all of these areas to be in sync, and the challenges addressed in each area to really be able to efficiently scale. So this is where MLOps comes in, and being able to provide that intersection between people, process, and technology that allows you to deliver faster, improve quality by adopting DevOps-like processes specifically for machine learning workloads and models. And MLOps relies on the base practices of DevOps, but it does apply some considerations that are very unique to machine learning, but still does focus on that intersection, or that optimal intersection between people, process, and technology that really allows you to scale. So that wraps up the top challenges and considerations when approaching those challenges when adopting machine learning workloads at scale. Hope this session was useful. Feel free to reach out anytime. Always happy to chat further.
Thanks so much, Shelbee. This was a great session, great overview. People, process, technology. It's not only technology, folks. I learned a lot in this session. We do have a question for you, Shelbee. Could you share some AWS data governance tool recommendations, how to get started with data governance on AWS?
With data governance, there is actually a good, if you're familiar with the AWS well-architected framework, there is an analytics lens that goes under that, that goes into There actually is a machine learning lens and an analytics lens. Both of them touch on data governance in kind of two different lenses, right? Analytics as well as machine learning. So I definitely recommend one of those, or actually both of those lens white papers as a starting point.
Perfect. And yeah, if you have any more questions, feel free to put them in the chat and feel free to reach out to Shelbee. Shelbee, thanks so much. It was a pleasure to have you.
Thank you all.
And I don't see any more questions coming here. So thanks, Shelbee.
Thank you.
And we'll switch over to our second talk for the day. And I welcome Mani and Farouk to the stage and take it over.
Yeah.
So we will learn about hierarchical forecasting.
Thank you, Anjay. And let's get started. Let me start sharing my screen first. So everyone can see my screen now?
Yes, perfect. And also, if you want to do a quick intro of yourself and
Yes.
and take it from there. Thank you.
Yeah, absolutely. So hi, everyone. I'm Mani Khanuja, and I'm Artificial Intelligence and Machine Learning Specialist Solution Architect at AWS. And today I will be covering hierarchical forecasting using Sagemaker along with my colleague Farouk Sabir, who's also an AI/ML specialist solution architect at AWS. So the way we'll go through the hierarchical forecasting is first we'll talk about the concepts of hierarchical forecasting. Why is it important? Some of the approaches that hierarchical forecasting needs are, the techniques behind it. And then we'll followed by a deep dive demo on how you can do hierarchical forecasting using Sagemaker with an open source package called scikit-hts. So with that, let's get started. So before we talk about, anything, we need to know what hierarchical forecasting is, right? So now when we talk about time series, now these time series can be, naturally disaggregated by various attributes of interest. They can be like product type or geographical divisions. So for example, if we have a product, let's say shoe, right? And we want to do some forecasting on shoe sales. So the total shoe sales can be disaggregated by country, then within each country by state, within each state by region, and so on down to the store level, right? And in this presentation, you can see this picture where we are showing the state-wise sample hierarchical structure, right? So since these time series are following a hierarchical aggregation structure, these are referred to as hierarchical time series. And it's a very common technique to produce disaggregated forecast based on these disaggregated time series. And we usually require the forecast to add up to the same level as our data, right? So we want our store forecast to add up to our city, like Austin in this case, and then all these cities level forecast to add up to our state level, which is Texas in this example, right? So that's what our goal is, that we want to generate coherent forecast at all levels, and we want to preserve the relationships between these individual forecasts. Now, what are some of the techniques using which we can do that? So let's talk about some theory behind it, right? So the first approach over here is the bottom-up forecast, bottom-up approach. In bottom-up, it's a simple method. In bottom-up, we start with the bottom level time series, right? And then we sum all those forecasts upwards in the structure. And that's how these produce the forecast for all levels in the structure, right? So an advantage of this particular approach is that we are forecasting at the bottom level. So there is no information lost during the aggregation. But on the other hand, these bottom level data, it can be quite noisy and therefore can be more challenging to model and forecast. So in order to overcome these challenges, we have another technique, which is called as top-down. So with top-down, we start with generating the forecast for the total series, like the top one, which is the root node, right? And then we disaggregate these down the hierarchy. So now the challenge really becomes is, how do we distribute the forecast between these nodes, which are at the bottom level, right? So for example, in our previous example over here, just referring to the diagram, that we have produced the forecast for Texas, but how do I know that how to distribute it between Austin, Dallas, Houston, and San Antonio, and then further down to the store level? So that becomes a challenge. And in order to overcome that, there are certain approaches. So one approach is the average historical proportions. Now, what we do in that is we compute the ratio of the historical data for the bottom level to the total time series value at the time. And then we average it over the entire time series, right? So that's one method. The second method is proportions of the historical averages, where we capture the average historical value of the bottom level series related to the average total aggregate. So with these ratios, that's how we can distribute the forecast between different levels. So again, coming back to our example from the Texas level, we can do it to city level, which is Austin, San Antonio, Houston, so on and so forth, right? So that's how we distribute. Now, this works fairly well and provides us with quite reliable forecast for the aggregate levels and is useful when you have low count data. But really, there is a one disadvantage, that you're losing information due to aggregation, as well as think about, since we are calculating one forecast at the top level and then we are distributing, right? So what about the time dynamics of these individual time series at the bottom level and the special events, the seasonality between these individual levels? So how do we take those into account and still follow our top-down approach? That's where the third approach, forecast proportions, comes into play. In this, what we'll do, we'll calculate the forecast at all the nodes, right? Starting from the beginning. So like, for example, we have Texas, we have the cities underneath, Austin, San Antonio, Houston, so on and so forth. So we'll calculate the forecast at all levels, right? And then what we'll do at one particular level, we'll calculate the proportion of we'll calculate the proportion of the ratio of that individual initial forecast at a particular level, right? So we get, so when we are talking about, let's get over here. So when we are talking about Austin, so we have calculated the individual forecast, and now we have ratio of all these individual forecasts at one particular level, right? So we then use this information to distribute the forecast at all the levels of the hierarchy, right? So that's what we do with the forecast proportions, and that takes into account the seasonality and the time dynamics of of individual time series, right? Then the third approach is the middle out. With middle out, as the name suggests, we'll start with the middle. So we'll start with the middle time series. In our case, it's the cities time series. So we'll start with the middle level. And then we can use bottom-up approach to do the forecast at the top level, or do the top-down approach to calculate the forecast of the at the bottom level, right? Sorry, at the time series which are below this middle out approach. So that's how we will generate the coherent forecast for the whole hierarchy. So these three approaches are used to calculate the forecast. And again, the goal is that we want to preserve the relationships when we are aggregating these forecasts. And we also want to follow, with the forecast, we also want to follow the same structure as it was in the data, that my bottom level forecasts are summing up to my previous levels, right? And then you would also say, okay, what's this ordinary least squares mentioned over here? So it just creates an estimator, and we try to minimize the error on this reconciliation weight or the proportion values. So that's what it does. And the good part is, whatever approaches that we have discussed so far, all these with this scikit-hts open source package, All these approaches can be implemented with different popular forecasting algorithms like ARIMA, FP profit, exponential smoothing. And that's why we are also using this scikit-hts. And let me give you a little flavor of the package itself, right? So HTS is a very popular package which was available in R, right? And now with the Python library, we can use scikit-hts. It's still in beta, but it works really well. And there are other planned features also, which you can visit on their website for coming up with other deep learning algorithms. But for now, these are the ones that they have been using. And this is what we have implemented on Sagemaker. So why Sagemaker? Because some of the advantages that we get when we do training on Sagemaker, that we can train multiple models in parallel. So we can have and compare those multiple models with experimentation and tracking, and then search for the best approach. So without the Sagemaker, all these things become very time consuming and tedious. So in our demo today, we'll be covering an end-to-end implementation of hierarchical forecasting, where we'll start with preparing the time series data, working with different experiments and trials. We'll use the sklearn estimator because we're using scikit-hts, and then we'll evaluate the best candidate, run the multiple algorithms, do some predictions, and show you the visualization of these forecast results. So Farouk, my colleague, will be giving the deep dive on the Sagemaker Studio implementation. So Farouk, over to you.
Yeah, thank you, Mani. Hi, everyone. I'm Farouk Saber. Like Mani, I'm also an AI and ML specialist solutions architect at AWS. Let me share my screen. Can you see my screen, I hope, on hierarchical forecasting code? Okay, good. Okay, so as Mani mentioned, we will show how to do hierarchical forecasting using scikit-hts on Sagemaker, taking the advantage of Sagemaker features such as Sagemaker experiments and starting different trials in parallel so that we can run for various hyperparameters and various for hierarchical forecasting methods like bottom up, top down, or any other method in parallel, and then aggregating, evaluating, and giving us the best model which we are going to then predict on the data, and then we're going to show the visualization results. So for this example, we created synthetic data for clothing category in retail, so I will show you this data briefly. So here we have a data point for each day starting from November 97 up to 2009. And we have 6 items: men's clothing, men's shoes, women's clothing, women's shoes, kids clothing, and kids shoes. And we have quantity of these items sold on a given day. So each of these is one data point in the time series. And then we have this data for state level as well as for region level. So there are multiple states in a region. Okay, and this, you can think of this as a hierarchy here, that at the top level you have sales for a particular category like men's clothing for the entire country, and then at the bottom below, at the level below that in the hierarchy, you have sales for example, a region like Mid-Atlantic region, and at the lowest level, you have sales for each state. Okay, so that's how you can think of the hierarchy in this case. Okay. So this code is also available on GitHub, so you can get this notebook and the associated stuff with it, data set, as well as other files from GitHub, and we will post that link in the chat. Okay. So starting from it, you may have seen the initial few cells in other examples if you are familiar with Sagemaker and Sagemaker Studio. Here in Sagemaker Studio, we are just setting up some of the packages. We are setting up the scikit-hts package. We are setting up the FP profit package and portal and some other packages. We are installing that and so that they are ready for our modeling and our visualizations. Okay. In the next few cells, I will go through them very quickly and try to focus more time on the actual time series forecasting part in Sagemaker. So here again, we are importing the packages for our project and specifying the S3 bucket, because our data is going to be in Amazon S3 bucket for from where it is going to pull the data for training and validation. Okay, starting from the next section, now we are actually preparing time series data. We are looking at what are the fields in this data set. We are reading using pandas, so we know that the date, their item, quantity, region, and country are the columns in their. Country is of course redundant, since we are this data set is for USA. And how we created this synthetic data is we created some trends, and then we added noise to it so that there is some variation, and then we added seasonality as well to it by copying and then data from one from one time frame to the next, and then shifting up, down, or adding some multiplicative component, and also by adding some random noise to it, so that there is a trend as well as there is some variation in that data along with seasonality. Okay, so you can see we have the size close to 388,000 samples in the data set. This is how the data looks like, as I've shown in the other window. Going through the next few cells, we are just cleansing the data. We are dropping null item IDs and as well as null timestamps, because we always, as you know, in any data science project in the data set, there are many times missing items or invalid items and invalid dates. So we are taking care of that and dropping that. And in the next couple of cells, we are actually what we are going through is we are using the pyplot to look at the time series data for some of these categories. So this is the aggregated data, which is total. Again, you can see that it's from sometime in November 97, end of November 97, up to 2009. So this is the aggregated data. You can think of it as the data at the top level of the hierarchy. The total quantity sale for this item, men's clothing, across all the states and regions in the US. You can see there is some trend here. There is some multiplicative factor you can see here as well, and then a little bit of seasonality too, and a lot of randomness in there for individual days. This is for kids clothing, women's clothing, kids shoes. You can see specifically here the trend here is going down. It's very close to like an exponential kind of decrease in the data itself, and there are a couple of other costs as well for women's shoes and men's shoes. Okay, in the next step, we are splitting our training and in our data sets into the training and test sets. So we are using everything before this April 2009 for training, and then after April 2009 for testing. This is how we are partitioning our data set. Again, we are showing here the training and the training, basically the training data in this table here. And this is only for men's clothing visualization. Okay, so moving on to the actual part of how to represent this data in a hierarchical format, and then being able to train the model and then evaluate. Okay. So scikit-hts, it requires data in a particular format. So right now our data is in long format. Right, as we saw in this in the actual data here, everything is arranged in the quantity is in one column, and everything for state, region, and item, they are just one row for one particular day. However, the scikit-hts package requires data in a format where each column is a time series of its own. So that's what, and then we have to create it in a way that that the hierarchy is represented in the data itself there. So that's what we are going to do in this next step here. This code is in here in this data set prep file here in the folder for our GitHub repository. So here I have displayed this file here, and what this file basically is doing is in this experiment, excuse me, we are only going to build a model for men's clothing, but you can change it. Right now we have it hard coded here, but you can change it. You can have it as a variable as well to do the same process for any other category as well. But here what we are doing is we are taking the men's clothing as a subset of the data for the entire time period, and then we are aggregating first on the region level and then on the total level. So what we are doing is we are creating the columns for each state, the quantity sold on a given day for each state, then for each region, and then of course we have a total value as well. So this is what this is doing here. It's just a few group by statements and basically aggregation statements, and using that we are actually building the hierarchy for our data set. And I am going to show you how it looks like in the next step. Okay, so this is now this data set, this pre-processing step that we did for being able to train the model using scikit-hts. This data looks like in this table here. As you can see, we have now for each state, for each day, for each state, this quantity, right? And we have also specified which region this state lies in. For example, Illinois lies in East North Central in our data set. So that's how we have created this label here. So this is like this for all the different states in here. So each of these columns is for a state, and we have appended the region name before that state. And then in the last 5 columns, we have the regions here. You can see Mid-Atlantic, South Central, Pacific, East, North Central, and New England. Now, this is the aggregated data for all the states for that given day in that region, and that we have also the total value here. Okay. So this data is now in the format that scikit-hts can understand and train the model, the various hierarchical forecasting models on that. And here we are also representing and showing hierarchy, how the data looks like now in our hierarchical structure, starting from the regions and going down to states. Okay. So now we are going to select 2 revision methods here, hierarchical forecasting methods, bottom up and average historical proportions, along with additive and multiplicative seasonality modes. You can select other revision methods as well, other hierarchical forecasting methods, as well as any of these seasonality modes in the scikit-hts package. We are creating now 4 jobs here that we are going to try for these 4 different combinations: additive, bottom up, additive, average handle, average historic proportions, and for multiplicative seasonality as well. Now we also have a training script, and I'm showing that here. In this training script, what we are doing is we are taking our data, this hierarchical structure data, we are sending it, we're dividing into training and test channel, and we are sending, we are starting a HTS regressor, which is in the scikit-hts package, and we are using this estimator for profit algorithm. You can of course try for ARIMA or any other method as well. And we are specifying that at a given time, the max number of jobs we can run is 4 in parallel. Okay. So these are some other parameters that scikit-hts requires, like how flexible you want your model to train on, like similar to the concept of bias and various trade-offs. So if you have this change point bias as a higher value, then you have more flexibility in the model. Okay, so here we are going to basically train on this using this script, using Sagemaker experiments, and then we also have an evaluation function for evaluating the total mean squared error for our data set. In the next cell, we are setting up a Sagemaker experiment. And in that experiment, we are actually starting the 4 trials, 1 trial for each of those 4 combinations for the hierarchical algorithm and the seasonality mode. We picked 2 hierarchical methods as well as 2 seasonality modes, additive and multiplicative. In the next in the next section, actually, what we are doing is we are specifying what metrics we want to look at. So we want to look at the total mean square error as well as the mean squared error divided by individual states and individual regions as well. And finally, we are creating the scikit-learn. We are using the scikit-learn estimator and using the STS regressor from the package along with the profit algorithm and our training script to start the training in Sagemaker experiment. Okay, and that experiment, when it's running in Sagemaker, we will see this once it is running and it's completed. It will show up here in Sagemaker experiments tab, and we can right-click on it and look at various metrics associated with each of the states and the total mean squared error as well. Okay, after that, we are actually evaluating our time series predictions for predicting values 90 days ahead. Okay, so this is just showing the results of training and where you can find the artifacts and what parameters it tried for actually training the model and the mean square error. And finally, since we are almost out of time, so I'm going to show you the results. Of course, this depends on our hyperparameters algorithms that we have picked, the seasonality modes, as well as how flexible we want the model to look like. So this orange one is the actual values, and the blue ones are the predicted values. This is for various regions, and also we have the plots for individual states. Here we have shown plots for a few of these regions and states here, but you can run them and visualize them once you download the code for all of these states. I think we have only 1 minute left. So thank you, everyone. If you have any questions, please feel free to ask.
Yes, thanks so much, Mani, and this was a great overview. We had a comment here, looks awesome. People were excited. We had one question here in the chat, and Mani already answered in the chat, but maybe you want to just briefly touch on it, elaborate a little bit. Does the hierarchy change a multivariate model to multiple single variate models?
Does the hierarchy change a multivariate model to? So this is sorry, go ahead. So this is working for a single variable, right? So Mani, do you have anything to add to it? Not sure if I understand. So are you at? Yeah, go ahead.
Yeah, I think for the question is that we have currently for this example, we are using single variable, but can we use multivariate models, or does it changes it into single, it changes the multivariate time series into different single variates, right? This is how I understand. So we can actually use multivariate models as well, and also use the exogenous variables to take into effect the time dynamics of each time series.
Yeah, that's correct. In scikit-hts, you can have you can also have that as well. And you may need to modify the notebook a little bit to make it work, but yeah, that can be done.
All right, and there's one more question just coming in. How long does the program take to run? So I guess referring to the notebook here.
So the training part, it takes around, so each job is run in parallel. So we have 4 different combinations we are running, and each model takes, I think, close to, for this particular data set, it was 12 minutes per model, I believe. It also depends on the type of virtual machine that we have selected to train your model. So that heavily depends on that as well. The one we picked took 12 minutes to train.
All right. Yeah, if you have any more questions, please put them here in the chat. Otherwise, I think this is a wrap. Thanks so much, Mani and Farouk. Was a great overview here. One of the few times we're actually talking about hierarchical forecasting. And just before everyone hops off here, quick reminder, we do have a webinar coming up next month in October 18. And following the theme of topics we don't talk as much about, we're gonna feature a topic on computer vision next month. So we will have a guest speaker, Shayan Saha, and he will talk about how to address data preprocessing bottlenecks in training computer vision models with Amazon Sagemaker, featuring NVIDIA DALI and Sagemaker Debugger. And then we'll also have another talk talking about leveraging Hugging Face on Sagemaker to create NLP models for contract review by Aaron Sangstecken and Heike Hotz. So make sure you're tuning in for October and get more details on those topics. Thanks so much for joining us today and hope to see you around soon. Thanks, everyone.